Hello everyone and welcome back to the Calculus Fun Room. In this video what we're going to do is formalize the ideas of limits, take a look at some limit laws and some examples. On the prior two videos ago, section 2.1 in Stewart's textbook, we took a look at an application of average velocity and instantaneous velocity. And in that process of going from an average to an instantaneous, we introduced the idea of a limit, and we saw what limits look like in a kind of visual, numerical manner in regards to those applications. And then in 2.2, we took a step back. We spoke a little more general mathematically. We looked at a bunch of different types of graphs. We did numerical limits as well. And in particular, we talked about what it meant for a limit to exist, that the one-sided limits had to equal each other. So in this video, what we're going to do again is kind of build on that conversation a little bit more. And we're focusing now on the generalizations of the mathematics behind these ideas of limits. Now remember, the limit process is kind of one of the most beautiful aspects of calculus, and it allows us to take average velocity and bring it to an instantaneous, and it'll provide a lot of other tools that we will use later in this course by which we use approximations to then get to a more precise value. So what you would typically see in the first page, if you will, of a textbook is introducing the first of the first 5 of many limit laws. So the first law says that the limit of a sum is equal to the sum of the limits. So what we're looking at here is we have two functions that we're adding, and we're in essence distributing the limit process. Now that is absolutely not a rigorous term to use here, because we can't really distribute processes like we do when we multiply numerical or algebraic expressions. But that first one says that a limit of a sum is the sum of the individual limits. And again, we're supposing that the limit of f and g already exist on their own, right? So that first sentence there says, suppose that c is a constant and the limit of f as x approaches a, and the limit of g as x approaches a exists. Right? Then each of these properties hold true. So the second one really says the same thing. The limit of a difference is the difference of the limits. Number 3 says the limit of a constant times a function is the constant times the limit of the function. So it's sometimes called the constant rule. We can in essence pull the constant out of the limit operator and then multiply it back on at the end of the limit process. Number 4 says the limit of a product is the product of the individual limits, and then similarly for number 5, the limit of a quotient is the quotient of the limits. I wrote these out beforehand real quick just to save a little bit of time. Feel free to pause the video here at this moment and write these limit laws down for yourself. And what we will do next is we'll take a look at an example where we apply these limit laws. In this first example, I paused the video real quick to sketch out graphs so we can take a look at a couple examples where we apply these limit laws. Now I did the best that I could sketching this graph without gridded paper. And let's go through this and talk about how we would apply these limit laws for this particular graph. So the first one that I'm stating is let's find the limit of f of x plus g of x as x approaches 2. So if we use the sum rule, right, the limit of f plus g, that's going to be the limit of f plus the limit of g, both as x approaches 2. So what I'm going to do then is look at the graph. What is the limit of f of x as x approaches 2? So f is the blue graph, and as we approach 2 here, the blue graph approaches 1. Right? So from the left-hand side, the function f right here, right, is approaching 1, and as we approach from the right-hand side, the limit is 1. Now the function value is equal to 2, but that doesn't matter. Remember, the limit, we never get to x equals 2. We only approach x equals 2. So from the left and from the right, the limit of g is equal to 1. And then now let's take a look at the limit of the g of x as x approaches 2. Now think I might have said that wrong a second ago. The limit of f as x approaches 2 is 1. Now I'm going to switch to red. We're going to look at the limit of g as x approaches 2. And again, without gridded graph paper, what I'm trying to indicate here is that x approaches 2 from the left and from the right. The g function is trying to get to 5. Now again, it doesn't matter that g actually equals 5 when x is equal to 2. We're just taking a look at a limit as x approaches 2, and g is trying to get to 5. So then the sum of the individual limits is going to be 6 in this case. Let's take a look at a second example. So in this example, let's say we want to take a look at the limit of, let's say, f of x times g of x. And we want to look at, let's say, x approaching, let's do 3. Oops, let's do 3. So again, the limit of a product is the product of the individual limits. So I'm going to switch color here. I'm going to go to blue to take a look at f of x. So if I look at, I apologize, x approaching 3. So down here at x equals 3, we're looking at the blue graph, which is f. And at x equals 3, when I approach from the right and from the left, f is trying to get to 1. And then we're going to multiply that to what the red graph g is doing as x approaches 3. So when I look at the red graph of g at x equals 3, again without graded graph paper, I'm trying to indicate that that is 4. So as we approach from the right and as we approach from the left, g is trying to get to 4. So we take the product of those two. 1 times 4 is 4. All right, let's take a look at a third example. So let's say in this example, we're going to take a limit of, let's do 3 times f of x over g of x, and let's let x approach 0. So again, I'm going to do the limit of a quotient being the quotient of the limits. So I'm going to take the limit of the numerator. I'm going to divide by the limit of the denominator, and I'm getting a little sloppy there for a minute. I left off x approaching 0 on the top and the bottom limit. And then in the numerator, I'm going to look at the limit of a constant times a function, and I'm going to pull the constant out and take the limit of the function and multiply those two, right? That was my constant rule. And again, I've gotten a little sloppy here. Those should both be as x goes to 0. So now we're going to take a look at each of those individual limits. So first, the top, what's the limit of f as x approaches 0? So f is my blue function. If we look over here, right, at x equals 0, my origin, as I approach from the left, it looks like f is trying to get to 2. As I approach from the right, f is trying to get to 2. So I'm getting 3 times 2. And then in red, what is x doing? What is g doing as x approaches 0? So my red graph, it looks like from the left and from the right, I'm trying to get to 4. So in that case, I have 6 over 4, which is 3 halves. Okay, let's do one more example here. Let's say number 4. We're going to take a limit of, let's say, 2 times f of x minus 5 times g of x as x approaches 5. Alright, so again, we're going to use our limit laws here, and we're going to say this is the limit of 2 times f of x minus the limit of 5 times g of x. And I probably could get a little bit efficient there and go ahead and just pull the 2 out in that very first step. But just to continue to have the conversation of each of those laws separately. So I'm approaching 5 for both of these limits. So again, I'm going to take a look at each of these limits separately. So the function f, when I look as x approaches 5, so I'm going to switch to blue. So as x approaches 5 from the left, we're trying to get to 2, and from the right, we're trying to get to 0. So this two-sided limit as x approaches 5, this does not exist. Now when I look at the limit of g does have a limit that exists as x approaches 5. So it looks like I tried to make this be the value of 6 there. So as we approach from the left, g is approaching 6. As we approach from the right, g is approaching 6. So I get, 5 times 6 here. Now, what I actually want to do in this case is take this just a little bit further, and let's look at the left-hand limit and the right-hand limit separately and see what we get here. So in other words, I'm going to take a look at, so I'm going to come back up and rewrite. So I'm going to take a look at the limit of 2 times f of x minus 5 times g of x. I'm just rewriting my problem, and I'm going to let x approach 5 from the left. And then I also want to take a look at that same thing, 2 times f of x minus 5 times g of x. And let's look as x approaches 5 from the right. So I'm going to go ahead and kind of skip the steps where I come all the way down to 2 times the limit of f of x as x approaches 5 from the left, and then minus 5 times limit of g of x as x approaches 5 from the left. So let's see what we get here in this case. So what is the limit of f as x approaches 5 from the left? And again, I'm looking at the blue graph. Right in front, x approaches 5 from the left. My f function is trying to get to 2. So I'm getting 2 times 2 here. And then what is the limit of g as x approaches 5 from the left? We said when we look at the red graph, that's trying to get to 6 up here. So we have 5 times 6. Now, because from the left, right, my limit of f does exist as a one-sided limit, then I'm going to go ahead and crunch this result, right? So I have 2 times 2, so I get 4 minus 30, so that's negative 26 there. Now if we come over here and we take a look as x approaches 5 from the right, and I'm going to go ahead and switch to blue, so I'm going to have 2 times the limit of f of x, and then I'm going to have minus 5 times the limit of g of x. I don't know why I kept all that in blue there. Let me switch this. I love OneNote. This is the coolest thing ever. Alright, so let's now take a look at, and remember, I'm going to go ahead and get a little sloppy here, okay? I really should be writing x approaching 5 from the right underneath each of those limits. Just want to have the conversation here. So as x approaches 5, so let me go ahead and write it, even though I said I was being lazy. So as x approaches 5 from the right on my blue graph, again, f is trying to get to 0. So I'm getting 2 times 0 minus, and then I'm going to get 5 times, and again, g as x approaches 5 from the right is trying to get to 6. So I'm getting 0 minus 30, and that's going to give me negative 30. So even in this scenario, we can see the right-hand limit and the left-hand limit are not equal to each other. Right? So since the one-sided limits, right, since the limit of x approaching 5 from the left, and I'm going to get lazy again and just write this out as a conversation. Since these two limits, in fact, let me get a little more efficient, and let me just say these are not equal. So since the one-sided limits are not equal, then the two-sided limit does not exist. This first example just illustrates our process in a more kind of big picture conversation. So instead of looking at a specific equation, a function, we're just focusing on the conversation visually from a graph. Now at this point we'll discuss a couple other properties of limits. So we saw those first 5. Let's say property 6. This is sometimes called the power rule. And it says if we're taking the limit of a function raised to an exponent, then we can look at the limit of the function, find that result, and raise it to that exponent. If we kind of take a look at a quick example here, suppose that I'm looking at the limit of some function raised to a power. Let's call it the cube power. And let's say that from the graph, and I'm just throwing stuff out here, let's say from the graph f of x is approaching, I don't know, 2. So we would be getting 2 cubed, which would give me 8. Now if I come back and look at this expression, right, that's a limit of a product, really, right? It's like the limit of f times f times f. I mean, that's what we're really looking at here. That's what the cubed means, right? So I could use my product rule in that case. Oops, the 3 isn't there anymore. F times f is x cubed, right? So in that case, I'm looking at the limit of f times the limit of f times the limit of f, right? And that is the limit of f all being cubed, okay? So not surprising that I can, in essence, push the limit symbol under the exponent. So again, coming back up to my property here, again, this is horribly not rigorous mathematical conversation here for a moment, but I'm in essence taking this limit and pushing it under the exponent, taking the limit of the function, then raising that result to the exponent. And this is typically called the power rule. Now there's also an analogous rule here, would be if I have the nth root of a function, I can, again, very lazily push the limit under the radical, evaluate the limit, then do the nth root of that result. And again, this shouldn't be very surprising, right? Remember, the nth root of a function is really a rational exponent, right? You know, square root of x is x to the 1/2, right? So, you know, nth root of something is the something to the 1/n. So 6 and 7 really tie together in the sense that these are really both rational exponents or integer exponents in that case. So another property you typically see written out explicitly is that the limit of a constant as x approaches any number is going to be just that constant. You know, if we think visually here, the graph of a constant, right? If I graph y equals c, so let's say, you know, here's the number 3, let's say, right? So if I graph y equals 3 or y equals a constant, that's a horizontal line. Right? So I can see if I approach x equals a, from the left I'm approaching c, from the right I'm approaching c. So again, no surprise that the limit of a constant is just that constant. And then usually at this point, the last thing that we would discuss here is what we call the direct substitution rule, sometimes the direct substitution property. So I'll go ahead and title this the direct substitution. So the direct substitution in essence says that the limit of a function as x approaches a is going to equal f at a. So in other words, I'm going to take the value that x approaches and just plug it into the function if f at a is defined. And so let's take a look at an example here. So let's suppose in this example, let's take a look at some equations instead of graphs, right? Let's focus a little more algebraic. So let's say I have the limit of x squared minus 3x plus 1 over 2x plus 5, and let's let x approach, let's say, 2. Let's go ahead and just totally illustrate all of these properties that we've looked at so far. So the first thing I would do then is take the limit of the quotient as being the quotient of the limits. So I'm taking a look at the limit of the numerator over the limit of the denominator. And then now let's go ahead and look at the numerator itself, and I'm going to take the limit of a sum or difference as the sum or difference of the limits. So in the numerator, I'm going to write this, and I'm going to run out of digital paper here pretty quick. So I'm going to go ahead and jump down to this line. So the numerator I'm going to write as the limit of x squared minus the limit of 3x and then plus the limit of 1. And let me go ahead and stay a little bit precise here. All of those limits are as x approaches 2. And then in the denominator, I'm going to have the limit of 2x and then plus the limit of 5. Again, that's the limit of a sum is the sum of the limits, and the limit of a difference is the difference of the limit. Now I'm going to go ahead at this point and throw two of my properties in together. So what I mean by that is when I look at this first term in the numerator, the limit of x squared, I'm going to go ahead and say this is the limit of x squared. So I'm going to use that power rule that we talked about. Then I'm going to take the 3 out of the limit as x approaches 2, and then I'm going to look at that just as the limit of the constant, which we'll use the constant rule, or the limit of a constant equaling that constant here in just a second. And then I'm going to take the limit of 2x and pull the 2 out, and then plus the limit of the constant as x approaches 2. So now I'm going to use the direct substitution rule that we just discussed. So in this first expression here, let me take out the yellow highlighter for a moment. So I'm going to plug x equals 2 into the x value. So the limit of x as x approaches 2, I plug in the 2 and I get the square. And then 3, and then I'm going to switch to the blue highlighter. Right? So I'm going to take x equals 2 and plug it into x, and I'm going to get 2. And then the limit of a constant is the constant. And then in the denominator, same thing. So I'm going to have 2 times, and I'm going to direct substitute 2 into my variable. So I'm going to get times 2, and then the limit of 5, limit of a constant, is just the constant. So now do the arithmetic here. So 2 squared is 4 minus 6 plus 1 all over 4 plus 5. So what do I get there? Negative 2 plus 1 is negative 1 over 9. Alright, so this example, if we take it step by step by step, we illustrate each of the properties of those limit laws, right? Each of those limit laws. Limit of a quotient is a quotient of the limits, and then the limit of a sum or a difference is the sum or difference of the limits, and then we used pulling the constant out of the limit process, and then in the end we used the direct substitution rule. Now what I want to do is come back up here, let me use blue, and let's take a look at our initial expression. What we could have done from the very beginning is just substituted x equals 2 right into that expression. If I want to think of x squared minus 3x plus 1 over 2x plus 5 as a function, right? If I were to graph that function, x equals 2 is in the domain of that function. Or the only thing I would have to really be concerned about there is, is the function undefined at x equals 2? Do I get division by 0 at x equals 2? And I don't. So because 2 is in the domain, I could just direct substitute right at that point. Let me zoom out just a hair here. So I'm going to swing down here, and I'm just going to go ahead and plug everything in, right? So I'm just going to direct substitute. So I'm going to end up with 2 squared minus 3 times 2 plus 1 all over 2 times 2 plus 5, which of course gives me negative 1/9 there as well. So the direct substitution law is wonderful. I mean, it basically just says as long as x, if I'm looking at the limit as x approaches a, as long as a is in the domain of my function, just plug it in and see what you get. Now, this is the general concept in this section, and there's a couple what did I just say? This is a general concept in this section, but there's a couple exceptions to this direct substitution rule. So the next couple examples I want to take a look at what those exceptions would be where I can't actually use the direct substitution rule. How do we get around that process? So in this next example, let's take a look at one of those scenarios where we have an exception, right, where we can't use one of those limit laws initially. So let's say we're taking a look at the limit of x squared minus 9 over x minus 3 as x approaches 3. Now if I try to do the direct substitution right away, notice I'm going to get division by 0. So I can't just plug in x equals 3. This isn't going to work. So in this scenario, and in all of the examples, all of the problems, exercises in this particular section, we're going to be able to do some algebraic manipulation to get the limit to work. Now in later sections that won't always be the case, and we'll discuss other techniques or methods to deal with those. But in this section, expect there to be some way to manipulate the function if direct substitution doesn't work right from the start. Now you probably notice already that the numerator factors as a difference of squares. So I'll go ahead and factor the numerator. And I can see in this case, and again, this is bad math terminology, but x minus 3 and the top and bottom factors cancel out. Remember, they don't really cancel. Right? X minus 3 divided by x minus 3 is 1. So I really simplify the expression, but a lot of times we get lazy and we call that canceling. So what I really end up with in this case after I simplify is the limit of x plus 3 as x approaches 3, and then at this point now I can use direct substitution. I can just plug the 3 in and see that I get 6 as that limit. Now something to make a note of here, that we have done a simplification, right? We have taken x squared minus 9 over x minus 3, and we simplified that to be just x plus 3. Now I just wrote the equality sign here, and this is a true statement as long as x is not equal to 3, right? Now, what we then said is the limit of x squared minus 9 over x minus 3 was equal to the limit of x plus 3. That's what we just did. Right? We basically said those limits are the same. So how is that valid? Right? If those expressions aren't equal to each other when x equals 3, right? How can the limit be valid? And so, think about this for a moment. A limit is we're getting close to 3. We're never actually getting 2x equals 3. So these two expressions are not equal to each other when x equals 3. But when we're close to x equals 3, right, as we approach 3, those two things are equal to each other. So that's why we can say those limits are equivalent. So usually at this point, if we say something along the lines, right, if some function f of x simplifies to a different expression g of x, then the limit of f is equal to the limit of g as x approaches a. And in fact, probably what I should say here is if f equals g for f not equal to a, I apologize, for x not equal to a, right, then the limit of f still equals the limit of g. So because we're not actually getting to x equals a, those limits are still going to be equal to each other. All right, another fun example to do here is to use the difference quotient. So we're going to, again, see this quite extensively a little bit later in the textbook. So let's say we're looking at the quotient 3 plus h squared minus 9 all over h as h goes to 0. Now if I try to plug h equals 0 directly into this expression, I'm going to get division by 0 here. So again, in this section, in the safe confines of this section, we're going to expect some algebraic manipulation to work here. So I'm going to FOIL out the numerator. So I'm going to square the first, multiply the 2, 3 times h is 3h, and then I double. And then I square the last, minus 9 all over h as h goes to 0. Again, we can see the 9s are going to subtract out to be 0. So I'm going to have then the limit as h approaches 0. Oops. So I'm left with 6h plus h squared over h. And then I can factor an h out of the numerator. And then we're going to get the h there to reduce. So I end up with the limit of 6 plus h as h goes to 0. Now I can finally use the direct substitution. 6 plus 0 is 6, and there's the result of our limit. Now, both of these examples illustrate something unique that we're going to delve into deeper in a later section really soon. And first of all, if we look at this expression that we're on here, if I tried to, let me come back up to my original expression. If I plug h equals 0 in right in the very beginning, notice what's going to happen. In the numerator, I'm going to get 9 minus 9. In the denominator, I'm going to get 0. So I have 0 over 0 in this case. Now, something we might do is incorrectly think that 0 over 0 is 1, and that is most definitely not the case. And in fact, in this case, 0 over 0 approaches 6. I don't want to say it equals 6, right? Because we're looking at a limit process. Now, if we come back up to the prior example, if I plug in x equals 3 here, again, I'm getting 0 over 0. And in this case, ironically, the limit also is 6. That just was totally coincidental. We definitely could get a different number there in that case, right? So just be cautious of that. The reason that I take a look at that, I have that conversation with you real quick, is this points out to us that when we have this expression 0 over 0, we sometimes get some unique behavior. And in this case, 0 over 0 is turning out to be a constant value. It's a limit that exists. Now, that's not always true. We could get 0 over 0 being something that doesn't exist. But in this section, right, we're going to see 0 over 0 having some algebraic cleanup process that can then get us to a limit that does exist. All right, let's take a look at one last example here where we do some algebra fun. So let's say we look at the square root of 4 plus h minus 2 all over h as h goes to 0. Now, I point out to you here that if we plug in h equals 0, in the numerator we're going to get 0, and in the denominator we're going to get 0. So, in this, again, the safe confines of the section, we might expect there to be some algebraic manipulation that could allow us to simplify that expression. And there is. So, what you'll notice in the homework is that when we have a radical, we can usually multiply top and bottom by that radical. Now, in this case, we have a radical that is part of a binomial, right? We have a radical minus 2. So you may remember from like an intermediate algebra course, one thing we can do is use the conjugate. So I'm going to do a little bit of side work here, just so I don't have to carry that limit symbol with me all the time. So check out what happens when we use the conjugate. So again, whenever I multiply a fraction, right, I gotta do the same thing to the top as I do in the bottom, because I'm really multiplying by the number 1. So I'm going to go ahead and multiply all of this out. So in the top, oh, and I said conjugate, that means you change the sign to positive. So if I multiply everything out in the top, I'm multiplying out a binomial, right? So I multiply the first, I'm going to get 4 plus h. I multiply the outside and the inside, and those are going to cancel out, right? That was the beauty of the conjugate. And then I multiply the last, and I get 4. On the denominator, I have h times root of 4 plus h plus 2. So, in this case then, let's go ahead and clean up the numerator. I'm going to get in the numerator 4 and minus 4, and I get just h. And then the denominator, I'm not going to distribute, and here's why. If I don't distribute there, notice now the h's reduce out of the top and the bottom, and I end up with just really 1 over square root of 4 plus h plus 2. So in a little bit more of a formal manner, we have the square root of 4 plus h minus 2 all over h. There's my original problem. That's going to equal the limit of, and then our simplified expression that we just ended up with. So now if I direct substitute into this, I'm going to get 1 over, so I get the square root of 4 plus 0. Square root of 4 is 2, plus 2, and I get 1/4 out of that expression. Alright, so I paused the video real quick and I brought up my graphing calculator, and I just wanted to explore the idea here. So in y1 I put my original expression that we were taking the limit of. Right? We were taking the limit of square root of 4 plus h minus 2 all divided by h. Right, as h went to 0, and then here in y2 was my simplified expression after all of that side work. We had 1 divided by square root of 4 plus h plus 2. Now obviously if I'm wanting to graph, I'm in function mode, I'm using the x variable here. So if I graph, I'm going to do a zoom decimal. If I graph, there's y1, there's y2, we can see they lie on top of each other. Of course, those two expressions are equal through our side work of algebraic manipulation. Now if I hit trace and I punch 0 into the first equation, so in y1, of course, when I plugged in 0, right, I got the division by 0. And notice that y equals blank, right? So it's undefined. Now if I hit my up or down arrow, I'll jump to y2. And we can see now on y2, of course, when I plug in h equals 0, x equals 0, I get y equals 1/4. And that was our limit that we got out of that result. One last example I'm going to take a look at here to wrap up this video. I wanted to scroll back up to the statement that we wrote here. I'm going to box in red. Right? So we had this statement that if f equals g, as long as x is an a, then the limit of f equals the limit of g as x approaches a. So something very similar that we can say there is if f is less than or equal to g of x, then the limit of f will be less than or equal to the limit of g. Man, I'm telling you, my hands are having a Monday. So if x approaches a, these limits are will have this relationship as long as f is less than g. If we think visually for a second, I'm going to pick two different colors. Like let's say, so what we're saying here is f is less than g. So f, I'm going to make my blue function, and it is smaller. So let's say here's the limit of, or here's the function f, and then g is larger, right? So g is somewhere up here. They don't have to be the same shape. In fact, I don't want to imply that, right? So let's say here's g. So as long as f is less than g, then at some point a, the limit of f is going to have a value that is smaller than the limit of g, whatever those two values are, right? So we can see visually in this manner that the limit of f will be less than the limit of g as long as f is less than g. So this allows us to make the statement that is called the squeeze theorem. So the squeeze theorem basically says something like this, is let's suppose that we know f is less than or equal to g, which is less than or equal to h. And we're going to say near x equals a. So as long as we're close to a, we know this relationship is true, and we know that the limit of the lower bound has the same limit of the upper bound. So let's say, f of x and h of x have the same limit. Then we can conclude that the limit of g of x must also be the same, must also be L. So in a visual manner, I'll do a quick rough sketch here. So f of x, again, I'm going to highlight in blue here, right? F is my lower function. Let's say here's f. And then h is my upper function. And actually, let me make this a little prettier, right? So let's say here's f, and we know that at x equals a, we have L as my limit. Then g is the upper function here, and also as x approaches a, the function h, I think I said g, the function h has a limit of L as well. So we're supposing that f is less than or equal to g, which is less than or equal to h. And the way that I like to read this is that h is between f and g, right? So g, I don't know why I keep saying the wrong letters. I apologize. G is between f and h. So G has an upper bound of h, and then G has a lower bound of f. So G is caught between f and h. Now I don't know what G looks like. Let's say it looks something like this. So it's caught between f and h. So here was f and here was h, and this is our function g. So if we know that that relationship is true, that g is caught between f and g, and we know that f and h have the same limit at a, then g must also have the same limit. G is being squeezed into the limit of L, and this is called the squeeze theorem. Now, the squeeze theorem isn't something we always want to use, but there's going to be some situations later in the semester where this will be the only way we can prove a particular limit. So let's take a look at an example where we would apply the squeeze theorem. In this last example, let's take a look at, we're doing the limit of, let's say we're taking a look at the limit of x cubed sine of 1 over x as x approaches 0. All right, now in this case, I would love if I could use the limit of the product as being the product of the limits. And then I'd love to be able to direct substitute. So in this first expression, limit of x cubed, I'm going to get 0 cubed. And in the second expression, I'm going to get the sine of 1 over 0, which obviously won't be defined. 1 over 0 is undefined, right? So as x goes to 0, I'm getting the sine of undefined, right? And that's undefined. All right, so taking out my calculator real quick and graphing the expression x cubed times sine of 1 over x, I can see visually that it looks like that expression is going to 0. Now what I want to be really careful of here is I don't want to say that 0 times anything is 0, because that is not necessarily always true. So just like we saw a couple minutes ago, 0 over 0, we got 6 out of that, right? But that isn't always necessarily true. So we just want to be careful here. Now, in this section, we're going to be told use the squeeze theorem to show this is true. Right? So we're introducing this idea and we're practicing this idea. And a little bit later in the textbook, we won't necessarily know that we need to use the squeeze theorem. We'll talk about how we can discover that. But the instruction here, which I didn't write, I just said verbally, is let's use the squeeze theorem to determine what this limit is, right? To evaluate this limit. So then the difficulty here really becomes, how do I find the bounds, right? How do I find the upper bound and the lower bound? And if we keep in mind this, right? Remember that the largest the sine function ever is, I'm going to scoot over here, the largest the sine function ever is 1, and the smallest the sine function ever is -1. Now, I want to say, sine of theta, let's say, right? So the sine of whatever is 1 or -1 at its peak value. So what I'm going to do then is I'm going to look at x cubed times sine of 1 over x. And the largest that sine ever is 1. So the largest that expression will ever be is 1 times x cubed, and then the smallest sine ever is -1, so the lower bound there is -x cubed. Now, because we're looking at the limit as x goes to 0, let's point out to ourselves that the limit of -x cubed, now I can direct substitute, 0 cubed is 0, and the limit of the upper bound is also 0. So we're satisfying the conditions of the squeeze theorem. We know that x cubed sine 1 over x has those bounds. We also can show quite easily that the lower bound and upper bound have the same limit. So we can conclude then that our expression we were trying to find the limit of is equal to 0. And I'll just say, by the squeeze theorem. So in summary, in this section, we have discussed limits in a very formal manner. We looked at the limit laws. We had quite a few limit laws that we looked at. We applied those limit laws graphically. We applied them algebraically. We mostly used the direct substitution rule in the end. That's the most efficient process. Then we talked about some situations where if the direct substitution rule doesn't work, that we could try some algebraic manipulation to clean up our expression, or in some situations we could use the squeeze theorem. This really wraps up everything that we would want to discuss in this section. In 2.4, the next video that we'll look at, we're going to look at a very formal, mathematical, rigorous definition of a limit. It's called the epsilon delta definition. I look forward to seeing you then.